Welcome back to the deep dive. Today, we're plunging into a topic that might sound a bit technical at first glance, but trust me, it's a foundational game changer for digital security and absolutely fascinating. We're going to embark on a deep dive into cryptographic agility. Imagine a world where your most sensitive digital locks don't just sit there static and, well, vulnerable, but can spontaneously upgrade themselves without you even noticing. Picture, like, a digital immune system constantly evolving, adapting to keep your most sensitive data safe against new threats, and even entirely new computing paradigms, all on the fly. That's essentially what we're talking about, the ability of our information systems to adapt, to pivot, and to stay ahead. It's not just a nice to have anymore. It's really a strategic imperative that could very well define who thrives in the digital future, especially as we look towards, a quantum-powered world.
Indeed, that analogy of a digital immune system is spot on. What we're discussing here is far more than just a technical feature or a checkbox to tick. It's a foundational shift in how we approach cybersecurity. It's about moving from a reactive stance, where we're constantly playing catch-up after a breach, to a proactive one. It's about building resilience and adaptability into the very fabric of our digital infrastructure, ensuring that our systems can evolve alongside, or maybe even ahead of, the sophisticated threats they face.
That paints a really clear picture. So, okay, let's break it down. What exactly is cryptographic agility? Why is it so vital right now? And what does it truly mean for how we protect our most sensitive information? Our mission today is to understand this concept inside and out, from its historical roots in that, well, endless arms race, to its critical role in facing the quantum era. We want to give you the insights you need to navigate this crucial and frankly unavoidable aspect of modern security. Hashtag tag one. Unpacking the what and why of cryptographic agility. So let's start at the very beginning. At its simplest, what are we talking about when we say cryptographic agility? What does it mean for a system or, I guess, an entire organization to be crypto-agile?
Right. At its core, cryptographic agility is the capacity of an information system to swiftly and efficiently switch between cryptographic primitives and algorithms, and crucially, without causing system disruption. Now, when I say primitives, I mean those fundamental building blocks of cryptography, things like, encryption algorithms, hashing functions that create unique digital fingerprints, or digital signature methods that verify identity.
Okay, the basic tools.
Exactly. Agility is about rapidly and seamlessly transition between these different cryptographic algorithms, keys, protocols, or even entire underlying mechanisms, without significant disruptions to operations, to security, or, importantly, to interoperability. You need things to keep working together. This flexibility is what allows an organization to remain resilient in a world of constant technological change and evolving threats, rather than being, locked into outdated, vulnerable methods.
That makes perfect sense. So it's about swapping out these digital parts without a major system breakdown. It's such a critical concept that even official bodies like the National Institute of Standards and Technology, NIST, have stepped in with a formal definition, haven't they?
They absolutely have. NIST formally defines it as the capabilities needed to replace and adapt cryptographic algorithms in protocols, application software, hardware, and infrastructures without interrupting the flow of a running system in order to achieve resiliency.
Without interrupting the flow, that's key.
Mhm. And what's crucial to understand here is that this is more than just a technical mandate. It's really a comprehensive conceptual framework for managing cryptographic risk in a dynamic threat environment. Think of it as a crucial incident response mechanism. When a system's cryptographic foundation is discovered to be vulnerable, agility dictates how quickly and smoothly you can pivot to a secure alternative.
Right, so it's part of your emergency plan almost.
In a way, yes. It's also important to distinguish this from general system evolution. While, typical system evolution is often driven by emerging business requirements or new features, crypto agility is a specialized discipline focused purely on the underlying security infrastructure. It requires dedicated and expert attention from security architects, system designers, and application developers. It's not just another feature update.
That distinction is really important. So, okay, for a system to be truly agile, beyond just the cryptographic elements themselves, there are some universal design principles at play, right? It's not just about the specific algorithms, but the fundamental architecture has to support it.
Precisely. If we connect this to the bigger picture of system design, for any functional component to be truly agile, cryptographic, or otherwise, it must satisfy three key conditions. First, there's interchangeability. The functions must be sufficiently similar to fulfill the same intended purpose. You can't, for example, swap a hashing algorithm for an encryption algorithm and expect the same security outcome. They need to serve the same fundamental purpose in a, comparable way.
Right, apples for apples, sort of.
Kind of, yeah. Second, diversity. The realized functions should exhibit meaningful distinctions. This could mean independent failure modes, meaning if one algorithm is compromised, its alternative isn't likely to fail in the exact same way. That's crucial. It also implies varying trade-offs, perhaps in speed versus security, which ensures robustness under changing conditions. You want to have genuinely different backup options, not just slightly modified versions of the same thing.
Okay, so real choice, real difference.
Exactly. And finally, switchability. The cost associated with transitioning between these functions must be low. This can be measured in time, financial resources, or administrative overhead. The goal is to avoid significant impact on the end user or the operational budget during the transition. Think of these not just as technical requirements, but as the fundamental litmus test for whether your organization can truly pivot without crashing. If you can't easily swap out a component, if you don't have genuinely diverse backup options, or if changing them costs a fortune, well then you're inadvertently building in rigidity, not agility.
So given all that, why is this capability no longer just a desirable technical feature, something nice to have, but a strategic necessity? What's truly at stake here for organizations and I guess even for individuals who rely on these systems?
Well, cryptographic agility is now a foundational layer upon which a truly resilient security posture is built. It fundamentally shifts an organization from a reactive security stance, which is often characterized by those costly, chaotic, and disruptive emergency responses we talked about, to a proactive one that anticipates and plans for the inevitable obsolescence of cryptographic algorithms.
Anticipates the inevitable. That's the key mindset shift.
It really is. This capability allows organizations to rapidly adapt to emerging threats, newly discovered vulnerabilities, and even evolving regulatory requirements. Think about things like those from the U.S. National Security Agency, the NSA, or the European Union's GDPR. If a new regulation demands a stronger encryption standard for certain data, an agile organization can implement it smoothly, avoiding heavy fines and, reputational damage.
Right, avoiding the panic mode.
Exactly. Consider sectors like finance, healthcare, government. Data breaches in these areas can have catastrophic consequences, not just financially, but for public trust, patient safety, even national security. In such environments, crypto-agility acts as a proactive defense mechanism. It significantly reduces the attack surface and enhances their long-term security posture. Without it, organizations are left scrambling, patching vulnerabilities under extreme pressure and scrutiny, which is both expensive and, frankly, fraught with risk. It's the difference between having a well-rehearsed fire drill and frantically trying to find the extinguishers while the building burns.
That's a vivid analogy. And is there one particular very current and, well, very looming threat that's amplifying this need for agility even more right now? Something that's really pushed this conversation to the absolute forefront?
Absolutely. The single most significant and immediate driver for cryptographic agility today is the impending threat of cryptographically relevant quantum computers. This is a threat that has the potential to render much of today's widely used public key cryptography obsolete, perhaps in a matter of minutes. As such, the urgent global transition to post-quantum cryptography serves as the ultimate real-world case study for the profound value and absolute necessity of agile design. It's not just about protecting against current threats, but future-proofing our entire digital society against a paradigm shift in computing power that is already, well, on the horizon.
Here's where it really hits home how long this problem has been around. This isn't a new challenge, is it? I mean, the history of cryptography itself seems to be this relentless cycle of invention, breaking, and reinvention. It's like an endless arms race.
That's absolutely right. It's a tale as old as time, or at least as old as the need for secret communication.
Yeah.
From the simple shift cipher used by Julius Caesar to hide military messages, to the complex rotors of the Enigma machine during World War II that baffled Allied code breakers for years. Every method of concealment has eventually faced a code breaker intent on breaking it. This perpetual obsolescence is driven by two primary relentless forces.
Okay, what are those?
The first is the discovery of subtle mathematical flaws within algorithms. Cryptanalysts, the digital locksmiths of our era, are constantly finding weaknesses. Weaknesses that make it easier to exploit an algorithm than simply trying every possible key, what we call a brute force attack. For example, a public compromise of SHA-0, a hashing algorithm, was demonstrated back in 2004, highlighting a fundamental flaw. Its successor, SHA-1, was later broken by a practical collision attack in 2017, which had profound implications for digital signatures.
Right, the collision attack, where two different things get the same fingerprint.
Exactly. The second, and often more relentless cause of obsolescence is the inexorable increase in computing power. As technology advances exponentially, algorithms with small key sizes, once considered perfectly secure, become vulnerable to exhaustive brute force attacks. This was the fate of the data encryption standard, or DES. Developed in the 1970s, its 56-bit key size was eventually susceptible to a brute force attack by 1997, famously demonstrated by the Electronic Frontier Foundation's DES cracker.
Wow, 56 bits sounds like nothing now.
It really does. This historical pattern confirms that no cryptographic algorithm can be considered secure indefinitely. If history is any guide, the code written today will almost certainly become vulnerable in the future. It's a constant arms race where the finish line keeps moving. Hashtag 2.2, the cybersecurity debt of non-agile systems.
So if obsolescence is inevitable, what happens when organizations don't have this agility built in? It sounds like they accumulate something rather ominous called cybersecurity debt. Can you tell us more about that concept?
Yes, exactly. This cybersecurity debt is a critical and growing problem. It's the accumulation of security risks from legacy systems and protocols that remain vulnerable long after they have been formally deprecated or, proven insecure. This raises an important question. Why do cryptographic transitions take so long, often decades? A close examination of past transitions illustrates this phenomenon vividly.
Yeah, you mentioned DES.
Right. While the advanced encryption standard AES was standardized as the successor to DES way back in 2001, its predecessor, triple DES or 3DES, was not formally disallowed in the financial sector until 2024.
23 years.
A staggering transition period, yeah. Similarly, the SHA-1 hash function was first deemed insecure in 2005. Organizations like Google began advocating for its deprecation as early as 2014, but a full phase-out deadline for all systems was not set until 2030.
Wow, so it's not like we don't have better option.
Not at all. This immense time lag isn't a reflection of a lack of technical alternatives. Rather, it is a direct consequence of the inherent difficulty of a mass transition in a non-agile ecosystem. The fundamental issue is that organizations and developers, in the absence of an agility-aware design, often hard-code specific algorithms directly into their applications and infrastructure. They literally embed MD5 or SHA-1 into the code itself.
That hard coding, it sounds like a recipe for a huge headache and a massive budget drain down the line. What's the typical solution in a non-agile system when an algorithm inevitably breaks? It sounds like a security team's worst nightmare.
It leads to what we call the painful rip-and-replace approach. When an algorithm fails, the reactive solution involves a laborious, costly, and extremely time-consuming process. First, you have to identify every single instance of the vulnerable code across your entire infrastructure, which can be massive. Then you have to replace it, which often means rebuilding applications from the ground up and finally issuing new patches across all your systems. This rip and replace is a direct result of a lack of agility, and it's enormously disruptive.
Just chaos, basically.
Pretty much. Consequently, organizations that cannot adapt quickly are forced to maintain outdated and vulnerable systems for extended periods, sometimes for years, simply to preserve backward compatibility with other systems or because the cost of replacement is just too high. This accumulates significant cybersecurity debt, leaving them exposed to known risks. The solution isn't just to react faster, because that's always an uphill battle. It's to design systems with agility from the outset, enabling a manageable phase transition rather than a disruptive and potentially catastrophic overhaul. Hashtag 2.3 lessons from historical case studies and real-world breaches.
Let's look at some real-world examples that really drive this home for our listeners. The fall of DES and the rise of AES is a classic, right? It perfectly illustrates that prolonged transition period you mentioned.
It is indeed a powerful illustration of the consequences of fixed, non-agile cryptography. DES, developed in the 70s once the U.S. government standard, became widely used. But its primary weakness was that small 56-bit key size. As computing power grew exponentially in the late 20th century, DES became increasingly vulnerable to those brute force attacks. It was officially broken by this method in '97, leading to a critical need for a replacement. This prompted NIST to launch a competition, which ultimately led to the selection of AES in 2001. Yet, despite AES being a global standard for decades, its predecessor, 3DES, was still used in the financial sector until as recently as 2024. This just shows that cryptographic transitions, even when risks are well understood and superior alternatives exist, can literally take a generation to complete due to immense organizational and technical inertia.
And the SHA-1 collision provides another critical lesson, because that was a different kind of failure, wasn't it? Not a brute force attack, but a fundamental mathematical weakness.
Absolutely. The SHA-1 hash function, widely used for digital signatures and file integrity checks, failed not due to brute force, but due to a fundamental mathematical vulnerability that allowed what's called a collision attack. This means two different pieces of data could produce the exact same cryptographic hash. Imagine two completely different documents that somehow end up with the same unique fingerprint.
That's bad. Very bad for trust.
Extremely bad. In 2017, Google and the CWI Institute demonstrated the first practical collision, crafting two different PDF documents that produced the same SHA-1 hash. The application was profound. An attacker could, in theory, trick a system into accepting a malicious file in place of a benign one if both had the same hash. Following this, major web browsers began aggressively phasing out support for SHA-1 signed TLS certificates, essentially saying, we can't trust this for website security anymore. But what's truly insightful here is the contextual nature of cryptographic security. While SHA-1 was definitively broken for applications requiring collision resistance, where you absolutely need every document to have a unique fingerprint, it continued to be used for other purposes, like in the popular version control system, Git. Git uses SHA-1 not primarily as a security feature against malicious alteration, but as a consistency check to ensure data integrity within its own system. The types of attacks that broke SHA-1 didn't affect its ability to function as an integrity check in that specific context.
Ah, okay. So the risk was different depending on how it was used.
Precisely. This demonstrates that a blanket, one-size-fits-all approach to cryptographic transitions is inefficient. True agility requires a nuanced understanding, allowing retirement for high-risk applications while potentially retaining it for lower-risk uses, thereby avoiding unnecessary and costly overhauls.
And beyond algorithms being mathematically broken or having fundamental weaknesses, we've also seen major failures due to simple mistakes or bad practices, right? Sometimes it's not the cutting-edge math, but the basic human element that causes the breach.
Indeed. The history of cryptographic failures is sadly replete with real-world examples that illustrate the consequences of poor design, improper implementation, and basic human error. The RockU compilation in 2021 and the Facebook incident in 2019, for instance, both reveal billions of user passwords stored in plain text or with weak hashing.
Plain text.
Yeah.
Wow.
These weren't sophisticated attacks on the underlying algorithms. They highlighted a fundamental lack of proper encryption, salting, and robust hashing in password storage practices. It was like leaving the key under the doormat. Another stark example is the Toyota supplier breach in 2022, where a subcontractor mistakenly published private encryption keys and sensitive credentials in a misconfigured GitHub repository. Yeah. These keys, intended to protect Toyota's data, were exposed for anyone to find. These examples demonstrate that cryptographic failure isn't limited to an algorithm being mathematically broken. It just as often results from improper implementation, mismanagement of secrets, and a lack of foundational security practices within an organization. Agility means not just changing algorithms, but changing them correctly and managing them securely.
So if hard-coding algorithms directly into systems is the root problem that creates this cybersecurity debt, how do we design systems to avoid that rigidity and build in agility from the ground up? What do agile architectural patterns actually look like? Because I imagine many listeners are thinking about their own systems, perhaps even some old code that use something like MD5 crypto service provider in C#.
That's a great practical example and gets right to the heart of the problem. The fundamental principle of an agile system is precisely that, the avoidance of hard-coded cryptographic algorithms. A non-agile system is typically tied to a specific algorithm or implementation, such as that MD5 crypto service provider class in C#, which necessitates a code change, recompilation, and a new patch whenever that algorithm needs to be updated. To achieve true agility, systems should instead be built on a modular architecture, where cryptographic components are isolated from core application logic.
Isolated. How do you do that practically?
Well, this is most effectively accomplished through the use of crypto application programming interfaces, or APIs. Crypto APIs abstract cryptographic functions, allowing developers to make the same high-level calls, for example, hash algorithm, create regardless of the underlying algorithm that's actually performing the work. The Microsoft .NET framework provides a classic example of this approach. By coding to an abstract base class like hash algorithm and using a friendly name for the algorithm, an application's cryptographic behavior is determined at runtime, not compile time. It's like telling your car go faster rather than specifying increase fuel injection by X% and adjust spark timing to Y degrees. The underlying system figures out the best, most up-to-date way to achieve go faster.
Okay, so the code asks for hashing, not specifically MD5 hashing.
Exactly. An administrator with the necessary permissions can then simply modify a configuration file, such as machine.config in the .NET world, to remap a friendly name like MD5 to a new, more secure algorithm like SHA-256. This enables a seamless transition without the need to rebuild, retest, and repatch the application. It's a powerful configuration-driven approach that solves the dilemma of being tied to a particular algorithm that might become vulnerable in the future. Hashtag TAGE 3.2, the role of a centralized PKI and automated key management.
Beyond the algorithms themselves, what about managing all the keys and certificates that underpin so much of our digital security? I imagine that's a massive challenge in a large organization and a crucial component of agility that often gets overlooked.
It absolutely is, and you're right, it's frequently underestimated. Manual management of keys and certificates in complex environments invariably leads to human error, massive inefficiencies, and significant operational costs.
Yeah.
This often results in what's referred to as key sprawl, where organizations completely lack a clear inventory and visibility into their cryptographic assets. Imagine having a massive ring with hundreds of unmarked keys, and you have no idea which one opens what door, or even if some of the locks still exist. It's a recipe for chaos and vulnerability, making any large-scale cryptographic transition a major, if not impossible, hurdle.
Yeah, flying blind, basically.
Completely. If we connect this to the bigger picture, a robust and centralized public key infrastructure, or PKI, is foundational to an agile enterprise. By automating the complete lifecycle of all digital certificates and keys, and this includes their discovery, issuance, renewal, provisioning, and revocation, a centralized PKI provides the necessary visibility and control for swift transitions. Such automation not only drastically reduces the risk of costly outages caused by expired certificates or mismanaged keys, but it also provides a streamlined mechanism for integrating new cryptographic technologies when the time comes, making the entire system much more adaptable and resilient to future changes. It's about knowing exactly what digital keys you have, where they are, and when they need to be changed.
This reminds me of how some common protocols have evolved over time. Older designs, like TLS 1.2, for example, offered a lot of flexibility in which ciphers to use, but sometimes that flexibility backfired, creating more problems than it solved, didn't it?
Exactly. Older cryptographic protocols, such as TLS 1.2, the Transport Layer Security Protocol that secures most internet communication, and the JSON Web Token, or JWT, standard, were indeed designed with a high degree of flexibility. They allowed for a wide range of cryptographic options and combinations to be negotiated between communicating parties. However, this flexibility, while seemingly beneficial, came with significant drawbacks.
Like what?
Well, the sheer number of cryptographic options increased the attack surface, creating the potential for bad interactions between different algorithms that were never intended to be used together. It also made it incredibly difficult to thoroughly test and review all possible algorithm combinations, leaving potential security gaps. Furthermore, such systems were highly vulnerable to downgrade attacks.
Ah, downgrade attacks, where they force you to use an older, weaker version.
Precisely. Where a malicious actor could force a communication to fall back to an older, weaker protocol version or a less secure algorithm. The infamous Poodley attack on TLS implementations, which could force systems to downgrade to SSL 3.0 from 1996, is a notorious example of this vulnerability. Attackers could exploit the abundance of options to find the weakest link.
So what does this all mean for modern protocols like TLS 1.3? Did the designers learn from that and simplify things to avoid those kinds of issues and create something more robust?
Yes, precisely. The designers of TLS 1.3, which is now the Internet's standard for secure communication, and other modern protocols like WireGuard, made a deliberate choice to simplify and significantly reduce cryptographic options. TLS 1.3, for instance, explicitly removed support for a long list of weak algorithms, such as RC4, and mandated the use of a limited number of strong modern ones, like authenticated encryption with associated data, or AEAD ciphers. These are critical because they don't just scramble your data. They also ensure it hasn't been tampered with, and that it's from an authentic source, essentially, both locking the door and checking the ID of anyone trying to get in.
So less choice, but stronger choices.
Exactly. What's truly insightful here is that this opinionated design approach, which intentionally limits agility in favor of a simplified, more secure architecture. It may seem to contradict the core principle of cryptographic agility we've been discussing, but it reveals a deeper truth about the nature of modern security. True cryptographic agility is not about supporting an endless array of options simultaneously, because the risk introduced by the exponential complexity of testing all algorithm combinations and the potential for a weak link to be exploited in a downgrade attack can far outweigh the benefits. Instead, the modern approach is about having a robust mechanism to swiftly and seamlessly replace a single, opinionated choice, the current best practice, with a new, equally opinionated and secure one when needed. The model, in essence, is not a wide-spanning matrix of choices, but a clean version chain of secure primitives. It's about being able to pivot completely and cleanly, rather than juggling many choices at once.
Okay, it sounds like there are fantastic technical solutions for cryptographic agility, architecturally speaking, but adopting them isn't always easy. What are some of the biggest technical barriers organizations face when trying to implement this kind of adaptable security, even if they want to?
Right, the reality on the ground can be challenging. The journey to cryptographic agility is indeed fraught with technical barriers, primarily due to the vast technical debt accumulated in legacy infrastructure. Many organizations, particularly those running critical national infrastructure, CNI, think power grids, water treatment plants, communications networks, and those managing industrial control systems, ICS, that operate factory floors or smart buildings, they're often still relying on legacy hardware. This hardware simply lacks compatibility with modern cryptographic standards.
So the old equipment just can't handle the new math?
Basically, yes. Hardware constraints present a significant hurdle. For instance, many operational technology OT devices common in these CNICS environments operate on microcontrollers with extremely limited processing power and memory. The computational demands of modern cryptographic algorithms, and especially the new post-quantum algorithms we'll discuss, can easily exceed the capabilities of this legacy hardware. Upgrades become impossible without wholesale replacement.
That sounds expensive and disruptive.
Hugely. Furthermore, devices with hard-coded or hardware-accelerated algorithms are particularly problematic. If flaws are found in their cryptographic implementations, they cannot be patched in the field. This means you can't simply send a software update. You need costly and time-consuming physical replacement of the hardware itself. Imagine having to rip out and install new chips or entire devices across thousands of locations. It's a massive undertaking. And then there are supply chain limitations, which can also create long-term dependencies on specific vendor roadmaps, significantly delaying security upgrades if those vendors aren't prioritizing agility or are slow to adopt new standards. Hashtag 4.2 organizational and governance challenges.
Beyond the hardware and software challenges, what about the organizational side? The human and process elements that often trip up even the best-laid technical plans. It feels like this is where true agility often hits its biggest roadblocks.
You've hit on a critical point. These are often the toughest hurdles to overcome because they touch on culture, budget, and expertise. This raises an important question for any organization. How can you secure what you don't even know you have? One of the most pressing challenges is the widespread lack of a centralized, live cryptographic inventory. Startlingly, only about 35% of organizations report maintaining such an inventory.
Only 35%, that's low.
It's worryingly low. This leads to that state of key sprawl, where visibility into their cryptographic ecosystem is completely clouded. It's incredibly difficult to manage cryptographic assets, assess compliance, or effectively plan for transition without a comprehensive up-to-date record of where every key algorithm and certificate resides across all their systems. It's like trying to secure a fortress when you don't know how many gates there are or who has the keys to them.
Yeah, you can't manage what you can't see.
Exactly. On top of that, there's a significant budget and expertise deficit. A staggering 67% of organizations struggle with a dedicated budget and personnel for cryptographic transitions, and nearly 60% lack the necessary in-house expertise to assess, plan, and implement agility effectively. Cryptography is a specialized field, and finding or training those experts is a long-term investment.
So not enough money, not enough people who know how to do it.
That's a big part of it. Finally, the absence of a central policy management authority responsible for establishing clear standards and defining accountability across different business units leads to a fractured and ultimately unmanageable cryptographic landscape. Without clear governance, different departments might adopt different, incompatible cryptographic practices, creating security silos and increasing overall risk. It creates a mess where no one truly owns the problem. Hashtag 4.3. The unique problem of distributed and resource-constrained environments.
Are there certain types of environments where achieving cryptographic agility is particularly challenging due to their very nature? What about, say, blockchain systems? They're inherently decentralized and operate in a very different way.
Absolutely. Achieving cryptographic agility is uniquely challenging in decentralized and resource-constrained systems, such as blockchain protocols. Traditional agility mechanisms, like cipher suite negotiation, where two communicating parties agree on an encryption method, are simply impractical in an unbounded distributed network.
Mm.
It's unrealistic to expect an unbounded number of nodes, all potentially operated by different entities, to negotiate cryptographic algorithms for each communication without massive overhead and potential for failure.
Yeah, getting everyone to agree sounds impossible.
It's extremely difficult. Furthermore, implementing a large-scale software update in a blockchain is inherently difficult because not all nodes upgrade at the same time, which can easily lead to protocol forks, effectively splitting the network and disrupting its integrity. You risk breaking the very thing you're trying to secure.
So the upgrade itself is a huge challenge.
And these technical hurdles are unfortunately compounded by a lack of business incentives. Many blockchain nodes and miners prioritize short-term gains, like transaction processing speed or mining rewards, over long-term security considerations. This means they might be reluctant to adopt updates that could momentarily slow down operations or require investment in new hardware, even if those updates are crucial for future security. What's truly insightful here is that this demonstrates that agility must be considered for each specific implementation environment. What works for a centralized enterprise with a clear chain of command might be completely unfeasible for a globally distributed, permissionless network, requiring bespoke and often more complex solutions to achieve even a semblance of agility.
Okay, let's pivot to the elephant in the room. If there's one topic that gets everyone's attention in cybersecurity right now, it's quantum computing. How does this looming threat directly relate to cryptographic agility, and why is it making this entire conversation so incredibly urgent?
Well, the single most significant driver for cryptographic agility today is precisely the looming threat of cryptographically relevant quantum computers. These machines, by exploiting the principles of quantum mechanics, will be able to solve complex mathematical problems that are currently computationally infeasible for classical computers. Specifically, they will be able to efficiently break the integer factorization and discrete logarithm problems that underpin nearly all of today's widely used public key cryptography algorithms like RSA, Diffie-Hellman, and elliptic curve cryptography, or ECC.
So the foundations of today's secure internet, basically.
Pretty much. These systems, which secure everything from your online banking to government communications, could be compromised potentially in a matter of minutes once a sufficiently powerful quantum computer is built. This is a game changer of epic proportions, an existential threat to our current digital security paradigm.
Scary stuff. But isn't this still years away?
Here's where it gets really interesting and concerning. The threat isn't just distant, it's immediate, due to what's called the harvest now, decrypt later attack. An adversary, whether a nation-state or a sophisticated criminal organization, can collect today's encrypted data and store it, patiently waiting for a sufficiently powerful quantum computer to become available to decrypt it in the future.
Ah, so they steal it now, break it later.
Exactly. This poses an immediate, tangible risk to any sensitive data that must remain confidential for more than, say, 5 years. Any confidential customer records, intellectual property, or long-term strategic plans encrypted today could be wide open to a quantum attack in the future, even if those quantum computers don't exist in their full capacity yet.
Okay, that really changes the timeline.
It does. We can frame this risk using a variation of Moscow's theorem. The time the data must remain secure, let's call it X, plus the time required for a transition to quantum-safe methods, Y, must be greater than the threat timeline for a quantum computer to break current encryption, Z. The urgency is such that the U.S. government has taken decisive action. Executive Order 14144, issued on January 16, 2025, formally ordered all government departments and agencies to begin their transitions to post-quantum cryptography within specified aggressive timeframes.
So governments are already mandating action.
Yes. And to address this global challenge, NIST has been leading a multi-year international effort to standardize new post-quantum cryptography, or PQC, algorithms. These include Crystal Kyber for key exchange, Crystals to lithium for digital signatures, and SLH-DSA, another signature scheme. These are the new digital bulwarks we'll rely on. Hashtag 5.2 hybrid cryptography as a bridge to the quantum era.
So, given the incredibly high stakes of quantum computers breaking everything, how do organizations even begin that transition? It sounds like a massive, potentially risky undertaking. Is there a way to bridge the gap without a sudden Big Bang migration that could be massively disruptive and potentially introduce new vulnerabilities itself?
Absolutely. A phased strategic approach is essential. And one of the primary strategies for risk mitigation in this interim period is the adoption of hybrid cryptography. What's truly insightful here is that this approach involves combining a classical, quantum-unsafe algorithm like ECDH, elliptic curve Diffie-Hellman, which is widely used today, with one of the new quantum-resistant algorithms, such as Crystal's Kyber. The goal is to ensure that the encrypted data is protected from both classical attacks, which are relevant today, and the anticipated quantum attacks of the future.
Sort of a belt and suspenders approach.
Exactly. Hybrid cryptography provides a crucial, pragmatic bridge to the post-quantum world. It allows organizations to test new standards and mitigate immediate risk without a disruptive, big bang migration that could introduce unforeseen vulnerabilities or operational downtime.
Okay, and how does that work technically? Are there different ways to do this hybrid thing?
Yes, there are two primary architectural patterns for hybrid cryptography, each with different implications for agility and security. The first is a layered approach. This essentially applies a new quantum-resistant algorithm over the existing classical cryptographic infrastructure. Think of like putting a new, stronger lock on a door that already has an old lock. The advantage here is that existing applications remain largely unchanged, and if any issues arise with the new quantum algorithms, perhaps a new flaw is discovered or the standard evolves, rollbacks are easier. It's often seen as more agile because it can be applied or removed without affecting the underlying application logic significantly.
Okay, layered makes sense. What's the other way?
The second is the composite approach. This is generally considered more secure from a purely cryptographic perspective, as it combines the keys from both classical and post-quantum algorithms into a single, super strong composite session key. An attacker would, theoretically, have to break both schemes, the classical and the quantum-resistant, to compromise the data. But this deeper integration makes it inherently more complex to design and implement, and arguably less cryptographically agile at a macro level for future changes, because ripping out one part of the deeply integrated composite is much harder.
So layered is more flexible, composite is maybe stronger but harder to change later. Trade-offs.
Exactly. Trade-offs, as always, in security.
And is NIST, the National Institute of Standards and Technology, on board with this hybrid approach as a stepping stone, given these trade-offs?
Yes, NIST explicitly supports hybrid modes as a valid and necessary initial step for migration. They recognize their role in providing a crucial safeguard against unforeseen vulnerabilities in the new quantum-resistant schemes. While those standards mature and undergo extensive scrutiny from the global cryptographic community, it's a prudent way to start. If we connect this to the bigger picture, the PQC transition isn't just a technical upgrade. It is a global-scale change management program. It will likely span multiple leadership cycles in most large organizations.
Yeah, this isn't a quick fix.
Not at all. The historical precedent of multi-decade transitions from SHA-1 to SHA-2 and DES to ATES clearly demonstrates that a lack of agility now will have immense catastrophic consequences for decades to come in the quantum era. An organization that has not built agility by design will be forced into a costly multi-year and potentially catastrophic reactive program.
Right.
While an agile organization can treat the transition as a manageable, phased upgrade, the PQC transition is the ultimate test of an organization's crypto agility, and the time to begin is absolutely unequivocally now.
So, for any organization listening, from a small business to a large enterprise, how do they even begin to assess their readiness for all this? How do they chart a practical course forward? Where do you even start when facing a challenge of this magnitude?
That's the million-dollar question, isn't it?
Yeah.
And fortunately, there's a roadmap, or at least the beginnings of one. NIST has highlighted the critical need for a crypto agility maturity model to help organizations assess their readiness for these inevitable cryptographic transitions. Such a model can help an organization move from a chaotic, ad hoc, and manual process where changes are made reactively and painfully to a fully automated, integrated, and strategic posture.
A maturity model, like steps from basic to advanced.
Exactly. The ultimate goal here is to reach a strategic level characterized by agility-aware design. This is where crypto agility is not an afterthought or a bolt-on solution, but a core evaluation criterion for all project proposals and security architectures from the very start. It's about baking it into the DNA of the system from day one.
So what does this all mean for you, the listener? What's the practical roadmap for achieving this kind of agility in your own organization, laid out in clear, actionable steps? Because it sounds like a marathon, not a sprint.
It absolutely is a marathon, but when you can start training for it today. Achieving crypto agility requires a structured, multi-phase strategic plan. It's not something you can just flip a switch for. Let's break it down. Phase 1. Discovery and inventory. This is the critical first step, and based on historical transitions, we estimate it takes about 6–12 months for most organizations, depending on their size and complexity. Activities here involve creating a comprehensive cryptographic bill of materials, or CBM.
CBO, like a software bill of materials, but for crypto.
Precisely. It's essentially an exhaustive list designed to identify all cryptographic dependencies across your organization. It means discovering every algorithm, key, certificate, and protocol in use, as well as the specific applications, devices, and communication flows they protect. Automated discovery tools are absolutely essential for achieving a complete and accurate view of your cryptographic landscape, especially in complex, distributed environments. Without this foundational knowledge, you are flying blind.
Okay, phase one. Know what you have. What's next?
Phase 2. Risk assessment and prioritization. Following the inventory, this phase also typically takes 6–12 months. Once you know what cryptographic assets you have, organizations must evaluate their data in terms of its sensitivity, its value to a potential adversary, and critically, its lifespan. This analysis should meticulously prioritize the systems that process the most valuable or long-lived data, particularly any data that must remain confidential for more than 5 years. As we discussed, this is the data immediately vulnerable to harvest now, decrypt later attacks, and it must be addressed first. This phase helps you focus your resources where they will have the greatest impact.
Prioritize based on risk and data lifespan. Makes sense. Then comes the actual doing.
Right. Phase 3. Phased implementation and migration. This is often the longest phase, estimated at 1 to 3+ years per system, depending on its complexity and criticality. With a prioritized list in hand, organizations can then select a migration strategy for each system. Options include in-place migration, which means carefully replacing vulnerable components directly within the existing system. Replatforming, which is moving to an entirely new platform that is designed with agility. Or even service retirement if a system is no longer critical or too costly to upgrade. It is absolutely essential to engage with suppliers and service providers early in this phase to ensure they are aligned with emerging standards like PQC and can provide timely updates and support. You can't do this alone. Your vendors are part of your crypto agility ecosystem.
Okay, long-term, phased work involving vendors. And the final phase.
Phase 4. Continuous monitoring and governance. This phase is ongoing because cryptographic agility is not a one-time project, but a continuous process. You never truly finish it. This involves implementing automated monitoring, conducting regular audits, and establishing clear policies to track all significant changes to the cryptographic landscape. Continuous monitoring helps detect outdated or weak algorithms before they become a significant risk, and it ensures ongoing compliance with evolving industry standards. Without this continuous feedback loop, even an agile system can slowly drift back into a non-agile, vulnerable state as new threats emerge and algorithms become deprecated. It's about maintaining that digital immune system we talked about. Hashtag 6.3 implementation best practices.
So as organizations look at this multi-year journey, what are some key best practices that encapsulate all these phases for them to keep in mind? What's the cheat sheet for success here?
Okay, a quick summary. Robust implementation involves several critical best practices that cut across all phases. First, assess an inventory. You must catalog all crypto assets using automated tools to gain complete visibility into your cryptographic ecosystem. Don't rely on spreadsheets, use specialized tools. Second, adopt modular designs. Use abstraction layers in both your code and, where possible, flexible hardware like FPGAs, field programmable gate arrays. Those are chips you can actually reprogram even after they're deployed, giving you hardware-level agility. This helps avoid hard coding.
Okay, inventory and modularity.
Third, automate management. Implement centralized crypto lifecycle management, or CLM, for keys and certificates to reduce human error and increase efficiency. Get the manual work out. Fourth, test and plan transitions. Start with non-critical systems. Use hybrid modes and sandbox environments to minimize disruption and validate your approach before rolling it out broadly. Don't boil the ocean. And finally, monitor and audit. Implement continuous vulnerability scanning and compliance checks. Use key performance indicators, or KPIs, specifically for agility to ensure a proactive response to new threats and evolving standards. Those 5 principles, inventory, modularity, automation, phased testing, continuous monitoring, are your guiding stars.
What an incredible deep dive into cryptographic agility. It's abundantly clear now that the idea of cryptographic algorithms as static, permanent solutions is, well, long gone. We're living in an era where continuous managed renewal is the only way forward to maintain digital security and resilience.
Exactly. Cryptographic agility is the strategic response to this inevitable reality. It's about building resilience into systems from the ground up, moving beyond that costly and reactive cycle of rip and replace. And as we saw with modern protocols like TLS 1.3, true agility isn't about supporting every possible algorithm under the sun. Instead, it's about building a flexible mechanism to seamlessly switch from one secure, opinionated choice to another when needed. It's about intelligent, dynamic adaptation at scale.
And with the impending, undeniable threat of quantum computing, this isn't just an option, it's an absolute immediate necessity. The transition to post-quantum cryptography is the ultimate test of an organization's agility, demanding a multi-year, multi-phase, and cross-functional effort that will literally define the security landscape for decades to come.
The journey to becoming crypto-agile must begin immediately. The alternative is to face the inevitable consequences of a catastrophic event, where an organization's most valuable, long-lived data is rendered insecure by a threat that was known and could have been mitigated. The time for action is now. Cryptographic agility will define who is prepared to thrive in the quantum era and beyond. It's no longer a choice, but a strategic imperative.
That's a powerful thought to leave you with, and one that resonates deeply after our conversation today. Consider what data you have within your organization today that absolutely must remain confidential for more than 5 years. Are you truly prepared for its quantum era future? We hope this deep dive has given you plenty to think about, armed you with critical knowledge, and perhaps even inspired you to explore what cryptographic agility means for your own digital world. Thanks for joining us for this deep dive. We'll catch you next time.